This is a solution to problem number 57, chapter 21. This is the chapter about heat engines and refrigerators from the 4th edition of the Knight book. We'll start with looking at the PV diagram, the PV cycle, pressure axis, volume axis, and I suppose we should specify the units. We'll talk about pressure in atmospheres, which is not the SI unit. The SI unit is the Pascal. On the graph, they give volume in cubic centimeters. And it's a simple PV cycle because there are only 3 curves. We've got an isotherm. We know how to analyze isotherms. An isochore, constant volume, and an isobar. So this should be pretty easy because we have special formulas for all 3 of these processes. We're probably not going to have to do any calculus. We'll label the 3 vertices here, which are really the 3 states involved in the cycle. 1, 2, and 3. That's supposed to be a 1. And some of the values of the pressure, volume, etc. are given for these states. So we're told in number 57 that temperature 1 is 300 Kelvin. So let's start right out the gate with a table of the state variables for the 3 states. So we'll have a column for state, a column for pressure, and we'll put the pressure in atmospheres. Later we're going to have to convert the volume in, let's do volume in cubic meters. It really doesn't matter as long as you label the units that you're using. Temperature, definitely in kelvins. So we've got 4 columns here, 1 specifying the state, 1 the pressure, the so much for a vertical line. And we've got 3 states, 1, 2, 3. And I just mentioned that the statement of the problem tells us that state 1 is at a temperature of 300 kelvins. Now the graph includes this information. They tell us that the first state is at a pressure of 1 atmosphere. So we can enter that in here as well. And we can also read the volume off of the plot. We're told that this is 600 cubic centimeters. And then of course this is 400. And they even give us the final, or the volume for state 2, 200. So some of these state variables we can read off of the graph, and then there's one that's given in the statement of the problem, the temperature. And I'm realizing that actually it's going to be annoying to measure volume in cubic meters. So let's switch this to cubic centimeters. I'm going to try to be fancy and delete this in one. No, there we go. So volume in cubic centimeters. I'm definitely a noob still with the use of the tablet and the stylus, so please be patient. Thank you. 600 is our initial volume. They're also telling us, I'll write this down here, that the ratio of the molar heat capacities, which we call gamma, that's Cp over Cv by definition, they tell us that that number is 1.25. Now, I'm going to quickly quote the rule for monatomic gases. Remember, actually at any temperature, there's only 3 degrees of freedom, the 3 translational degrees. So that means there's a 3 in the denominator and a 5. You go up by 2 in the numerator. 5 over 3 times r. Am I doing that? No, there's no r there. Just 5/3, which of course is 1.66 repeating. And then for diatomic at normal temperatures, there's 5 degrees of freedom, 3 translational and 2 rotational. So we put the 5 in the denominator and then a 7 up top, and that's the 1.4. Well, this specific heat ratio, gamma, is neither of those numbers. 1.25 is neither. So this is not a diatomic gas and it's not a monatomic. It's something different. But because of this definition, gamma as the ratio of the heat capacities, we can actually solve for both of those molar specific heats. So over here, I'm going to remind you that Cp is Cv plus R. So really, gamma is Cv plus R over Cv. And if we distribute Cv with division, that's 1 plus R over Cv. So let's solve that equation for Cv. Let's see here. I get R over Cv equals 1 minus gamma. And just take the reciprocal to get Cv equals R over 1 minus gamma. And I think I did something wrong here, because 1 minus gamma would be a negative number, and molar specific heats are not negative. So what's wrong with my algebra here? Oh, why did I put a minus sign? This is, of course, a plus sign. My bad. Change this back to a... Yeah, so this should actually be gamma. Whoops. This should be gamma minus 1. Okay. Yeah, so this... That's really cool that it knows I want to delete that. This is actually gamma minus 1. That's something you could just throw on your note card or memorize if you're really good at that. We're going to use that later. But let's plop in numbers right now. 8.31 over, well, 1.25 minus 1 is 0.25. And can I pull up my handy dandy calculator here? Yeah. So let's see here. 8.31 divided by 0.25, or basically multiplied by 4. Well, not basically, that's exactly what it is. 33.24. Well, that's rather high. Okay, moving on. Let's go back to the table. We'd like to complete this table. And I'm realizing I haven't made the best use of space here. So I'm going to have to do some scrolling. Can I zoom out? Oh, check that out. Let's finish the second row. Well, the first thing we should probably find out is how many moles we're dealing with, because we're probably going to need that at some point. So we use the per-inert law, the ideal gas law, PV over RT, and we need to evaluate this at a particular state. And since we have the most information about state 1, I'll say P1V1 over RT1. And I'm actually going to cheat and not use the calculator here, because I have this calculation off to the side. You should find that we're dealing with 0.0244 moles of this strange gas that has an interesting ratio of molar specific heats. What's next? Yeah, let's complete the PVT table. So for state 2, well, let's look at this process right here. Going from state, what is that? Going from state 1 to state 2. That's an isothermal process. And we know that for an isothermal process, the temperature is the same. So if you look at the ideal gas law and you separate everything that changes from everything that doesn't, put everything that does change on one side, you're going to find that PV is constant. PV is constant for an isothermal process, which means P1V1 must equal P2V2, and we can solve that for pressure 2. because we know the volumes. Those are in the graph of the PV cycle. So P2 is P1 times the ratio of the volumes. Well, the graph tells us that the initial volume, V1, is 600, and then we compress down to 200. So the ratio is 6 over 2 or 3 over 1, so it's really 1 atmosphere times the ratio 3. In other words, we end at 3 atmospheres. Later, we'll probably have to convert that into pascals, but we'll put that into the table in atmospheres. We know the volume from the graph, it's 200. And remember, this was an isothermal process, so the temperature didn't change. So filling out this table is not going to be too difficult. Now for process 2 to 3, it's getting a little cluttered here. This is an isobaric process. The pressure stays the same. So if you put everything in the ideal gas law that could change on one side, you're going to have P over T. Nope, that's not right. Pressure is constant. So T over V. T over V is the constant quantity here. Did I do that right? Yeah. So that means T2 over V2 has to be the same as T3 over V3. And we're interested in knowing, well, let's see, from the graph, having trouble scrolling here. Oh, come on. From the graph, well, the pressure is the same as it was before. It's that 3 atmospheres. And we know the final volume. We don't know the final temperature. So we're solving for T3. T3, evidently, is you take the ratio of the volumes and multiply by T2. And if we look at the graph, we're going from 200 cubic centimeters back up to 600. So the volume is increasing by 3. Now, if you think about it, in general, when you allow a gas to increase its volume, you would expect the pressure to drop, and yet we want the pressure to stay the same. So the temperature must also go up to compensate. And that's why the temperature needs to be 6 over 2 or 3 times what it was for state 2. And that's going to bring us up to 900 kelvins. So I think we can complete the table now. The pressure is still 3 atmospheres because that was an isobaric process. We're back at 600 cubic centimeters, but now the temperature is at 900. So for this particular problem, completing the PVT table wasn't very difficult. We also know the number of moles, and we calculated C sub V. To get C sub P, you would just add R to C sub V. In part A, what the problem is actually asking for is the power output of this engine. We're told that the engine operates at 20 cycles per second. So what we need to do is figure out the work output in each cycle. We'll find that number in joules, and then just multiply that by 20 to find how many joules per second of work, that useful work that this engine is doing, and that'll be the power output. So I'm going to scroll down, way down here, and remind you about the overall energy flow diagram that you should be thinking about when you analyze a heat engine. So there always has to be some quantity of heat, QH, that's drawn from a hot reservoir. So if this heat engine is, for instance, the internal combustion engine in your car, then the hot reservoir would be the mixture of fuel products, combustion products, and air after the spark plugs ignite the fuel-air mixture. It's going to be really hot inside the engine. I don't know, a few hundred degrees Celsius. And you're drawing heat out of that so-called hot reservoir, and we call that quantity of heat QH. And you want to memorize that QH is always a positive number. Of that quantity of heat, some of it, unfortunately only some of it, actually goes out as useful work. The whole point of the engine is this arrow right here. This is mechanical work for the case of your car. It's supposed to make your wheels turn and drive your car forward. And I didn't draw this very well. Let's see here. Unfortunately, often more than half of QH just gets dumped right back into the cold reservoir. Oops, that's what we call the waste heat. And there's no way around it. There's no way to avoid wasting some of the heat. There's a limit on the percentage of the heat that can be used for useful work. So this is the, we need to, your book calls it various things. I'll call it work out. Sometimes your solutions manual calls it work per cycle. This is the total work done for the entire cycle. And we're going to have to compute that as the sum of various individual works, some of them positive, some of them negative. So this is what we call QC. It's also important to remember QC is always a positive number. Oftentimes when we use the letter Q by itself, it can be positive or negative depending on whether heat is flowing into the gas or out of the gas. I say gas because all of the heat engines that we analyze in this chapter use a gas, an ideal gas, as their working substance, even though at a power plant, inside the turbine, you've got steam, a mixture of steam and liquid water, and that's more complicated to analyze. You'd have to take a more advanced class. So Q in general can be positive or negative, but QH and QC are always positive numbers. Okay, so we define efficiency, eta, it's the Greek letter eta, as the amount of useful work done by the engine per cycle, the heat engine, compared to the amount of heat that was actually taken from the hot reservoir. For instance, let's say you burn some gasoline in your engine and you release 100 joules of heat energy from that chemical reaction, 100 joules. If you only get 20 joules of mechanical work output to make your car go forward, 20 out of 100, that would be only a 20% efficiency, which is kind of typical, as I understand. So definitely have this picture in your mind. If you're talking about refrigerators, the diagram is going to look similar to this, but the arrows are reversed. But let's actually go about now computing this quantity. So if we scroll back up to the PV cycle, can I change the color of my pen? Let's go with the red pen. Okay, cool. All right, I'm gonna draw arrows showing the direction of heat flow in each of these three processes. There's three processes in this PV cycle. So as we go from state 1 to 2, we're compressing the gas. So just imagine taking a volume of gas and squeezing it into a smaller box. In general, as you squeeze a gas, wouldn't it tend to heat up? And yet, in this case, we're doing an isothermal process. So the only way for the gas to stay at the same temperature while you compress it is for heat to flow out. So I'm going to draw a red arrow indicating that the Q for this process is a negative number. Heat is flowing out in order to maintain a constant temperature. Then as we go from 2 to 3, well, that's where the gas is expanding. That's where the useful work is being done. This would be like when the piston inside the cylinder of your automobile engine is going down. So the volume of gas inside the cylinder is expanding and doing useful work. And generally, when gases expand, wouldn't they tend to cool off? If they were insulated from their environment and the gas was expanding, it would be dropping in temperature. And yet, you can see from the graph, we're clearly going from well, we've already calculated. We're going from 300 kelvins here to 900 kelvins here. So how is it that the gas itself is doing positive work? So Ws is positive, and yet it's still increasing in temperature. That must mean that there's heat flowing in. So Q here is going to be a positive number. And then for process 3 to 1, when we go from 3 back to 1, there's no work being done because the volume is constant. So you've just got a box of gas with constant volume, and somehow it's cooling off. Well, that must mean because heat is flowing out. So later, when we want to calculate QH is the heat that flows in. That's just going to be, see, I don't think you can see my pointer, unfortunately. That's going to be this arrow at the top. That's QH. And QC will be the sum of the magnitudes of these two Q's. Both of these Q's are negative, so we'll add up their absolute values, and that will be QC. But right now, let's make a table. So for every heat engine that you analyze, you're going to make a table like this. You can have a column for, let's go back to the black pen. You're going to have a column for process. If you're unlucky, you'll have 4 processes. This one's easier. And individually, you'll want to calculate the heat transferred, the work done, and I'm going to talk about the work done by the system. You could look at it either way, work done on the gas or work done by the gas. We'll go with work done by the gas, WS for system. And then lastly, the change in thermal energy, because it's going to be interesting to talk about all 3 of these. Same procedure, every problem for heat engines. You're always going to make this table to organize your work. In some of the other videos, I did it with a spreadsheet, which is nice, but you don't get to use a computer during an exam, do you? So what are the processes? There's 1 to 2, 2 to 3, and then back to 1. Leave yourself some room to write these numbers. Obviously, preparing a table like this that's legible is going to allow me to give you as much partial credit as I can. Okay, so from 1 to 2, well, you might as well start with the easy ones, right? Because oftentimes, 1 or more of these quantities is 0. 1 to 2 is an isothermal process. And remember, for an ideal gas, this is not true for all systems, but for an ideal gas, the thermal energy is totally determined by the temperature. So if the temperature is not changing, then neither is the thermal energy. So there's no change in thermal energy. Let's go to the work next, because hopefully you remember that there's a formula for the work done in an isothermal process. You guys remember work done by the system. Maybe I should emphasize I'm looking at process 1 to 2 right now. The work done by the system is the integral of PDV. If this was the work done on the system, you'd have to stick a minus sign in there. Use the ideal gas law to rewrite P as nRT over V. And I'm going to pull out the nRT since the temperature is constant in an isothermal process. Think back to calculus. The antiderivative of 1 over V is the natural log. And then when you evaluate at the upper and lower limits, that's the final volume and the initial volume, you get the ratio. Well, you're going to get natural log of final volume minus natural log of initial volume, but log A minus log B is the log of the quotient. So this reduces to nRT, and I'll call it temperature 1, same as temperature 2, times the natural log of the ratio of final volume, that's V2, over V1. And let me consult my work off to the side here, because keep in mind that volume 2 is 200 and volume 1 is 600. So this ratio here is actually a number less than 1. And when you take the natural log of a number less than 1, like 0.5 or 0.8, you're going to get a negative number. So that's telling us that the work done is negative. nRT is a positive quantity, and then when we multiply by the natural log of a number less than 1, which is going to give us overall a negative work done by the system. Now, does that make sense? Yeah, because we're compressing the gas. If the gas is being compressed, then the work done by the gas is negative. All right, and you should find that this number is, I'm going to pause for a second. Okay, the reason I got stuck is because in my work off to the side, well, I'm consulting the publisher's solutions. They actually, instead of nRT, they used PV, P1V1, which is fine because PV equals nRT, right? You could use either. And what they found from this calculation was negative 66.8 joules, but let's see if we can confirm it. I'm going to do it this way and see if we get the same number. So let me pull up the calculator. Okay. Oh, great, there's no natural log button here. Man, there's no log button at all. This calculator sucks. So I'm going to have to find another way to do this. I'll just narrate while I use my $10 Casio. Love this Casio. And it's solar powered, so I got to wait like 10 seconds for this thing to turn on. Okay. So I'm going to use the nRT version. Well, let me do the log first. V2 over V1, isn't that 1/3? The final volume is 1/3 of the initial volume. So 1 divided by 3, hit equals, and I'll take the natural log of that. I do get a negative number. Then I multiply by the number of moles, which was 0.0244 times 8.31 times that initial temperature of 300 kelvins. And I do get the same number that the publisher got. This comes out to negative 66.8. And I'm going to keep numbers to the nearest hundredths place. Later I can round. So now I can plop that into the table. Negative 66.83. And it's just understood that my numbers are in joules. I don't want to have to write the units every time. I mean, you could emphasize right here. You probably should, that you're stating work in joules. And then to find Q, well, depending on the process, you might be able to use the definition of the molar specific heats, CV or CP. However, this is an isothermal process, so it's neither constant pressure nor constant volume. So there is no NCAT type formula that we can use for Q. The only time you can use NCAT is if it's constant volume or constant pressure. In any other situation, you're going to have to combine the first law of thermodynamics with your other equations like the ideal gas law. So that's what we'll do right now. So for Q, let's recognize the following. When you let heat flow into a gas, it can either allow the gas to do work, or it can change the gas's thermal energy. This is the version of the first law that's most useful for this chapter on heat engines. And we already concluded that the thermal energy change is 0 because it's isothermal. So Q and WS are numerically equal. See how easy this was for this particular process. Often you're going to find that one of these quantities is pretty easy to calculate. In this case, 2 were easy. Q and delta E thermal. Moving on to process 2 to 3. So I've copy-pasted the PV diagram again down here. Let's continue analyzing process 2 to 3. And we'll start with the work because that one's easy. Remember, for an isobaric process, well, for any process, the work done by the system is the integral of P dV, but if the pressure is constant, you can pull P out, and to integrate dV means just find the total change in volume, so it's P delta V. And here's where we're going to have to use SI units. So if I recall, the pressure at the top there is 3 atmospheres, so that's going to be 3 times 101.3 kilopascals. And the change in volume, we go from 200 to 600, so that's an increase of 400 cubic centimeters, which is 400 millionths of a cubic meter. And we know that SI in means SI out, so the work will come out in joules. And I'm going to check this on my calculadora. 3 times 101.3 times 10 to the third times 400 millionths. Do I get the same number as the publisher? Yes, 121.56 joules of work. Let's scroll up and put that in the table. 121.56. Can we easily determine any of these other quantities? Well, the temperature is changing, so there's going to be a non-zero change in thermal energy. Off the top of my head, nothing occurs to me for calculating that easily, but for Q, this is one of those special processes. If it's constant pressure or constant volume, you can use NCAT. So let's go down here, and we're going to need capital C sub P. We need the molar specific heat for constant pressure. And remember, that's C sub V plus R. I think I already calculated C sub V. So C sub P will be 33.24 plus R, 8.31. So we should have 41.55. I'm going to try to memorize that. There's some units there. I won't write them here. 41.55. So down here, we'll say that the heat for process 2 to 3, 41.55, is NCAT. So N C sub P times delta T, excuse me. So T3 minus T2. NCAT. Where this number is that 41.55. Okay, I'm going to do this on the calculator. The number of moles from before was 0.0244. I multiply by 41.55. And then the temperature change, we go from, remember we calculated this, from 300 kelvins up to 900. So that's a temperature change of 600 kelvins. And I find 608.29 joules, which matches the publisher's value. Great. 608.29. I probably could get away with just keeping the tenths place. This is a little annoying. But it's more satisfying when you can see that the numbers agree exactly, which you might miss if you do too much rounding. Okay, well, remember, anytime you've got 2 of these quantities, Q, W, and delta E thermal, any 2 will allow you to calculate the third using the first law. That's what the first law is all about, energy conservation. So now that we know the first 2, remember Q equals work plus delta E thermal. Remember my first law diet program? The food that you eat can go to 2 places, or two effects. It can allow you to exercise or get fatter, one of the 2. In this case, we're solving for delta E thermal, Q minus WS. So I'll take those 608 joules that were absorbed from the hot reservoir. And notice the problem doesn't specify what this engine looks like. There's no mention of what materials it's made out of, how big it is, the shape. We don't care. We're just analyzing the PV cycle. So of those 608 joules, only 121 in this part were used for useful work, leaving 486 to raise the internal energy. 486.73. We're making progress here. 486.73. So the gas increased its energy, which means the temperature had to go up. We know the temperature goes up. It goes from 300 to 900. Last process, 3 to 1. Before we even begin here, let's think, is there any easy? Should any of these be easy? Yeah. Isochoric process, there's no change in volume. You can't be doing any work if your volume isn't changing. So this one's cake. And then we just have to decide which of these to do Q or delta E thermal, because once we've got one, we can find the other from the first law. And maybe this is a good time to remind you that the super important point from chapter 20, I believe, for any process, hang on, for any process at all, even if it's not constant volume, you can still use this equation. The change in thermal energy is always NCV delta T. Hopefully you saw this in your book, I believe in chapter 20. You can always use this even if the volume wasn't actually constant during the process. Now, in this case, the volume is constant, so of course it makes sense to use it. But even if it's an adiabatic process or a constant pressure process, you can still use this, because you'll notice this is not the definition of heat capacity. If I put a Q here, if I was talking about the heat, then the equation would only be applicable for a constant volume process. Now, but if I write delta E thermal, it's true for any process, which can be useful. Sometimes when you're determining Q, WS, and delta E thermal, sometimes the easiest thing is to calculate delta E thermal using this equation. In fact, if you go back, you could probably redo part of this problem by calculating delta E thermal rather than the work or the heat. There's often more than one way to do it, and sometimes you can do both as a check. So let's, for this final process, 3 back to 1, let's calculate delta E thermal using this equation. That's going to be the 0.0244 moles times the constant volume heat capacity. And remember, this one's weird. We had to calculate CV using the given value of gamma. This is not a diatomic gas. It's not monatomic. We found above that CV was 33.24. And the temperature difference, well, it goes from 900 back down to 300. So that's a drop of 600 kelvins. This is going to come out in joules, of course. I'll plug this in, 0.0244 times 33.24 times 600. And I find that the thermal energy drops by negative 486.63 joules. Let's put that in the table, 486.63. Negative 486.63. And I'm already seeing that I must have rounded at some point, and those rounding errors have accumulated, because I know that that these two numbers should actually be the same in magnitude. Because when you add them up, you're supposed to find that the change in thermal energy for the complete cycle is 0. Obviously, right? If you bring a gas from state 1 around the cycle all the way back to state 1, the temperature, or the thermal energy at the end has to be the thermal energy at the beginning. That's something you should memorize about these heat engine cycles. The total, the net delta E thermal should always be 0. In fact, I didn't leave room here for total. So let me, since we've already done the work, I'm going to select all this garbage and get it out of the way. Goodbye, garbage. And I'll add a row in my table. You definitely want to include this row in your accounting. Anytime you make this table, have one final row for the totals. How do I get rid of this arrow? Get out of here. Oh, come on. No! Okay, so totes. Well, we're not done with this table yet, are we? The third row, we still need to find the heat Q. Well, there's two ways to do it now. We could say that the heat in this case, because it's a constant volume process, we can use this equation. Right? You can only write this if the process actually is constant volume. You can always write this no matter what the process is. Okay, you're probably getting bored because I keep repeating this. It's the same right side of the equation, right? So evidently Q equals delta E thermal in this case. But we can also see that from looking at the first law, because in general, Q is delta E thermal plus the work. And for an isochoric process, the work is 0. So of course, Q and delta E thermal are the same. That's two ways of saying that they're the same number. $486.6. I'm running out of room there. All right, now we can add up all these numbers. I'm going to cheat and fudge this and just say that these add up to 0 for the work. Got to use my calculator. 121.56, subtract 66.83. So in one cycle of this heat engine, the engine does 54.73 joules of work. And we would call this is the work out, or you could call it the work per cycle. So sometimes during the cycle, the gas is doing negative work when it's being compressed, and sometimes it's doing positive work when it's expanding. And you have to add those two together to find the useful output work. And for Q, this total is not terribly important. Let's go ahead and calculate it. So I'm going to add up all the Q's in the Q column. We've got a negative 66.83 plus 608.29 minus 486.63, and I get positive 54.83. That's the total heat. And again, that's not the most important quantity here, but it is useful to look at because notice that it comes out almost exactly the same as the total work output. They should be exactly the same. The difference is rounding error. And that's because for the total cycle, you can also apply the first law. Remember, this is the first law written from the point of view of the gas, of the system. We applied the first law to each of these three processes individually, but you can also apply it to the entire cycle. And remember, for the whole cycle, the net change in thermal energy is 0. So the total heat taken up by the gas, that includes positive and negative contributions, must equal the total net work done, which we tend to call work out. And they do. So that's a good check. You really want to complete the entire table, because if you don't find at the end that delta E thermal is 0, or you don't find that these two numbers are the same, that alerts you that you made a mistake somewhere. Okay, now the other thing we should determine is QH. QH is the sum of all of the positive Q's. And we know from the diagram, we already thought about this, only one of the Q's is positive. That's from 2 to 3. This is when heat is entering the system. So that would be the positive number in the Q table. That's the 608. What is it? 608.29. I'll just call it 608.3 joules. And QC is the sum of all the negative Q's. It's the total heat dumped to the so-called cold reservoir. So for your automobile, that would be the cooler air outside the vehicle. That heat gets dumped through the exhaust pipe, but also under the hood. Some of it goes from the manifold, I guess, into the air under the hood. And then there's the radiator. You get the idea. So when we sum up the two negative Q's, so here's what you do. They're both negative numbers, 66.83 with a minus sign, plus 486.63 with a minus sign. And at the end, I get negative 553. Just throw away the minus sign, because QC refers to the magnitude of the heat dumped. So it's positive 553.5 joules. So you can see most of the 608 joules, most of the 608 joules that were absorbed just get dumped right back into the environment. What a waste. And the useful work output is 54. So that's another check. For the whole cycle, let's check that work out. This is another equation that you should know how to use. It's the total heat absorbed minus the total heat rejected. I'll put a question mark here because we're curious to see whether that actually happens. So if I take the 608.3 joules and subtract the heat that was rejected, I do in fact get the 54.8 joules of net work that were done, which we already calculated right here. So it's satisfying to see that all the numbers agree, and it's almost mysterious if you think about it. Like, all these numbers, if you do the problem right, they always come out correctly and they're consistent with each other. So, you know, should that be mysterious? That it shouldn't be, I guess. If you really learn this material in depth and went over it over and over again, you probably have some way of seeing that, you know, the way the equations work. Of course it has to come out like that. I don't think I'm at that level yet because I still find it slightly mysterious that the numbers always come out consistent. Is there anything left to do in this problem? Well, we can calculate the efficiency. That's easy. Just take the output work of 54.7. I'll do this right here. I think I have a little bit of space left. The efficiency per cycle, every cycle's the same as the useful output work over the heat absorbed, and that's going to be the 54.7 or 8 joules compared to the 608 that are absorbed. This is getting really crowded here. Let me separate this garbage from the other garbage. Oh, my solar powered calculator. What happened? It's not even working. Okay. 54.8 divided by 608. Whoa, 9% efficiency? What a lousy engine. This is definitely not made in the USA. Or maybe it is, I don't know. Just not a very efficient cycle, and that isn't the number that the publisher got. But lastly, remember they were asking for the power. We know that each cycle does 54.7 or 54.8 joules of work. So the power output equals 54.8 joules per cycle. And you guys know this, right? A lot of motors, the cylinders or the pistons, they're going up and down like hundreds of times per second. You can find videos on YouTube where they cut away an engine, put some kind of thick plastic over it, and you can actually watch the fuel exploding and watch the pistons go up and down in slow-mo. It's quite remarkable devices. And there are 20 cycles per second. And notice how cycles cancel and we come out with joules per second, which is wattage. So this is 1096 watts. About the wattage of your microwave oven, which means this is not a suitable engine for running a vehicle. That's way too little power. Even a human being could develop that much power. Like when you're running upstairs, that's like a kilowatt. So this is not going to push a vehicle uphill or get it up to 60 miles an hour. The last thing we can say here, one of the things that the second law of thermodynamics tells us is that heat will only ever flow from a warmer object to a cooler object. So if you look at this part of the PV cycle, we've got heat flowing into the gas. If heat is flowing into the gas, then whatever the gas is in contact with, you know, the hot reservoir, it has to be warmer than the gas. So as the gas goes from 2 to 3 along this path, it's warming from 300 to 900 kelvins. In fact, I'm going to draw the isotherm through state 3. This hyperbola, every point on this hyperbola would be at a temperature of 900 kelvins. So if heat is still flowing into the gas as it approaches 900 kelvins, then the hot reservoir must be hotter than 900 kelvins. So we can say, if I can find some space here, we can say that whatever the temperature of the hot reservoir is, it must be greater than 900 kelvins. Otherwise, you wouldn't have heat flowing into the gas. It would be flowing out of the gas. And it's a little murky sometimes, like what really is the hot reservoir, because for the case of the internal combustion engine, the high temperature reservoir really would be the combustion products after you ignite the gasoline, but that's in the same physical space as the gas. The gas is in the cylinders, and so is the hot combustion products. So it's a little weird to separate the gas from the reservoir because they occupy the same space. Your book doesn't really address that. I don't know how to make that less murky, but let's also look at the other two processes. Heat's flowing out as we cool from 900 back down to 300, and then we stay at 300 from process 1 to 2. But if heat is flowing out of the gas all the way down to 300 kelvins, then it must be in contact with something that's cooler than 300 kelvins. If the cold reservoir wasn't cooler than 300, then heat could not flow from the gas out. It would be flowing into the gas. So we know that the cold reservoir temperature has to be less than 300. And for the case of an automobile engine, that makes sense because 300 kelvins is around body temperature, and when you're driving, the outside air is generally cooler than that. Now, if you were driving in really hot air, I mean, sometimes the air outside is hotter than 100 degrees, but actually that's not a good example because for an automobile engine, the temperatures inside are going to be much hotter than 300 kelvins. The gas inside is much hotter than 300 kelvins. So you wouldn't need a cold temperature of less than 300 kelvins. In any case, that's probably all we can say about this problem. Redundancy is good. If you can calculate things multiple ways, that's a good check. You need two tables. You need to have your ideal gas table where you put all the values of the state variables for each state. And if there were 4 states, this table is going to be bigger, 4 rows. At some point, you need to show the number of moles, show the 2 molar specific heats. You're probably going to need those. If one of these processes was adiabatic, you'd have to use some additional results that we didn't talk about. The second table you need is your first law table. You need Q, W, S, and delta E thermal. Every problem, same procedure. So the only difference from one problem to the other would be the shape of the PV cycle. And if you had an adiabat, again, you'd use different formulas. There might even be a process where you have to use a little calculus. Like if one of the processes was a straight line that was tilted, you could actually use some calculus to find the work done. You could integrate pressure over volume. That would be a little more challenging, but one piece of advice, make up a problem for yourself. Draw a PV cycle that's got 3 or 4 sides. I'm not going to give you one with 5 sides. That would be torture. Pick your 4 or 3 processes so that you can actually analyze them. So a mixture of isocores, isotherms, isobars, maybe an adiabat, maybe a straight line, and just solve it yourself. Because then if you do it right, the numbers will always come out right. All right, cheerio.